Hello class, I am Happy Narang, your subject of soil science. Today I am going to cover the topic that is chemical properties of soil. So we will be discussing these following points in this session: chemical composition of soil, ion exchange, soil pH, development and properties of acid soil, soil buffer capacity, significant and management of soil pH, effects of flooding in chemical properties. Soil is the thin layer of organic and inorganic materials that covers the earth's rocky surface. Soil is a mixture of organic matter, minerals, gases, liquids, and organisms that together support life. Basic soil properties can be divided into three categories: physical properties, that is texture, structure, bulk, density, etc. Chemical properties, salinity, pH, organic matter, mineral content, etc. Biological properties, biomass, biodiversity, etc. Soil chemistry is the collaboration of various chemical components that exist among all practices, as well as in the soil solution, the water sustained by soil. Chemical properties with aspects. One of the three components of balanced soil is chemical composition. Essential elements for chemically balanced soil. Both macronutrients and micronutrients need to be in balance. The pH of soil should match the need of the plants. The salt content of the soil should be low. Difficult to alter soil buffer capacity. Cation exchange capacity, in short we can say CEC, measures the soil's capacity to hold onto cations. Now comes chemical composition of the soil. Top four elements: carbon, hydrogen, nitrogen, oxygen. Macronutrients: phosphorus, sulfur, calcium, potassium, magnesium. Micronutrients or trace elements: boron, copper, iron, manganese, zinc, chlorine. Neutral pH 6.3 to 6.8 is ideal for most plants. This table shows the chemical composition, oxides, and value in percentage. SiO2 25.46, Al2O3 31.10, Fe2O3 35.53, CO2 7.91. Ion exchange is a cyclic process. That means the exchange of ions on soil surface with ions in soil solution. Ion exchange involves cations and anions that are absorbed from solution onto negatively and positively charged surfaces, respectively. Such ions are readily replaced or exchanged by other ions in the soil solution of similar charge, and thus are described by the term ion exchange. 4th, 1990. There are two types of ions. They are cations and anions. Cation exchange is greater abundance in soil than anion exchange. Cation exchange capacity is the value of a soil to indicate how much cation nutrients have the soil. Cation exchange is the interchange between a cation in solution and another cation on the surface of any negatively charged material, such as clay colloid or organic colloid. Assume for purposes of illustration that X represents a negatively charged exchanger that has absorbed a sodium ion Na, producing NaX when placed in a solution containing KCl. The following cation exchange reaction occurs as shown in the figure. In the reaction, K plus in solution replaced or exchanged for absorbed exchangeable Na, resulting in putting the absorbed Na in solution and leaving K absorbed as Kx. Cations are adsorbed and exchanged on a chemically equivalent basis, that is, 1 K plus replaces 1 Na and 2 K plus are required to replace or exchange for one Ca++. There are many cations in soil, but all are not absorbed in same amount. There is an sequence, that is, calcium is greater than manganese, manganese is greater than potash, potash is greater than sodium. Percentage is calcium 80%, magnesium 15%, potash 1.8%, and sodium is 1%. CEC is high in clay soil and low in sandy soil, because in clay soil organic matter is high, and by this figure you can observe it. Anion exchange capacity. Anion exchange sites arise from the protonation of hydroxides on the edges of silicate clays and on the surfaces of oxidic clays. The anion exchange capacity is inversely related to soil pH and is perhaps of greatest importance in acid soils dominated by oxidic clays. Nitrate is very weakly absorbed in soils and as consequence remains in the soil solution, where it is very susceptible to leaching and removal from soils. In general, plant absorbs as many anions as cations. The availability to plants of the anions nitrate, phosphate, and sulfate is related to mineralization from organic matter as well as anion exchange. Ion exchange capacity versus soil pH. CEC and AEC both depend on soil pH because pH indicates the soil character, as the soil is acidic or basic. To make valid comparison of CEC and AEC between soils and various materials, it is necessary to make the determination of CEC at a common pH. The CEC is positively correlated with pH. Therefore, acid salts have a CEC is then the maximum potential CEC. On the other hand, AEC is negatively correlated with pH. The CEC at the salt's current pH is called the effective cation exchange capacity. In short, we can say ECEC. The relative proportion of acidic or basic ions on the exchange sites determines the soil's pH value. Sandy soils with lower pH are more subject to leaching of nutrients. Nutrients. Soil is made of many components. Among them, organic matter is an important part of soil's nutrient. In organic matter, there stand some cations and anions. These cations are mainly known as nutrients. Of the cations, 4-cation is very important as nutrient because these cations are needed in plant growth, food, and many other physical habits. The sodium may be absorbed by plants, may substitute for some potassium, but sodium is not considered an essential element. Soil pH. The pH is a negative logarithm of hydrogen ion activity, and soil pH is a measure of soil's alkalinity or acidity. The pH of a soil is one of the most important properties involved in plant growth. Soil pH is usually measured in a standard suspension of 1:0.5 weight to volume of soil in distilled water on a dilute solution of calcium chloride. Determination of soil pH. Soil pH is commonly determined by mixing 1 part of soil with 2 parts of distilled water or neutral salt solution. Occasional mixing over a period of 30 minutes to allow soil and water to approach an equilibrium condition, and measuring the pH of the soil water suspension using a pH meter. The common range of soil pH is 4 to 10. There are some sources of alkalinity. Carbonate hydrolysis. It is the hydrolysis of calcium carbonate produces OH, which contributes to alkalinity in soils. CaCO3 plus H2O is equal to Ca2 plus HCO3 minus plus OH minus. Calcium carbonate is only slightly soluble, and this reaction can produce a soil pH as high as 8.3, assuming equilibrium with atmospheric carbon dioxide. In calcareous soils, carbonate hydrolysis controls soil pH. When a soil contains Na2CO3, the pH may be as high as 10 or more, which is caused by the greater solubility of Na2CO3 and greater production of OH minus by hydrolysis. In a similar manner, mineral weathering. The weathering of many primary minerals, however, contributes to alkalinity. For example, the hydrolysis of anorthe, that is calcium feldspar, produces a moderately strong base 3CaAl2Si2O8 plus 6H2O is equal to HAl4Si6O10 and bracket OS2 plus 3CaOS2. The generalized weathering reaction in which Am represents metal ions such as calcium, magnesium, potassium or sodium is Am silicate mineral plus H2O is equal to H minus silicate mineral plus Am plus OH minus. Sources of acidity. The following processes contribute to acidity in the soil. In all soils, respiration by roots and other soil organisms produces carbon dioxide that reacts with water to form carbonic acids H2CO3. This is a weak acid which contributes H plus to the soil solution. Acidity is produced when organic matter is mineralized because organic acids are formed and the mineralized nitrogen and sulfur are oxidized to nitric and sulfuric acid respectively. Natural or normal precipitation reacts with carbon dioxide of the atmosphere, and the carbonic acid formed gives natural precipitation a pH of about 5.6. The results of these reactions add acidity continuously to soils. Leaching of the basic cations, that is calcium, magnesium, potassium and sodium, results in their replacement by Al3 plus and H plus, and soils then become acid. This effect is brought about by hydrolysis when H plus ions would be generated through the following reaction. Al3 plus H gives AlOH plus plus H plus hydroxyaluminium. Positively charged hydroxyaluminium species may undergo further hydrolysis to produce additional H ions, leading to higher soil acidity. AlOH2 plus plus 2H2O gives AlOH plus 2H plus gibbsite. Against soils of acidic character are generally rich in calcium and magnesium because calcium and magnesium may precipitate as carbonate, increasing the buffering capacity of the solution. Ca2 plus CO2 plus H2O gives CO3 plus 2H plus. A general pattern, however, is that water-dominated soils of humid regions, have low pH values because their content of organic and carbonic acids is often subject to replenishing and recharge by rainfall. Under arid conditions, however, minerals which are salts of weak acids and strong bases would dominate the system, producing higher levels of alkalinity and causing the soil pH to raise to values between 9 and 10 or even more. Soil pH values above 10 may indicate contamination with strong bases such as NaOH, COS2. In soils with a pH of 7, there is a balance in the processes or reactions that produce alkalinity and acidity. On the central US Great Plains, this occurs with about 26 inches, or we can say 65 centimeter of annual precipitation. and the dominant upland soils are quite fertile for agricultural crops. The relationship between annual precipitation, the leaching of carbonates and soil pH has shown in the following figure. You can observe it by this figure. Development and properties of acid soils are role of aluminium after leaching has removed the carbonates. A progressive loss of XMG, XCA, XK and XNA occurs as leaching continues. Subsequent hydrolysis of the released Al3 plus produces H plus. Al3 plus H2O is equal to AlOH2 plus H. Hydroxy aluminium from the preceding reaction hydrolyzes to produce additional H plus AlOH2 plus 2H2O is equal to AlOH3 plus 2H plus. Acid rain effects is a environmental problem caused due to rapid industrialization. Acid rain has become invisible threat to rivers, lakes and forests. The basic component of acid rain are nitric acid and sulfuric acid. Soils that contain limestone and calcium carbonate can neutralize the acids. This causes natural or ordinary precipitation to be acid and have a pH of about 5.6. Leaching pushes the ions deeper in the soil so the plant's roots can't reach them. Now comes soil buffer capacity. In chemistry, buffer capacity is the amount of acid or base a buffered solution can soak up before its pH will start to change in significant. The buffer capacity of a soil is important in determining how its pH will change. Features: various minerals in soil have to buffer against changes in pH when an acid or base is added. At high pH, calcium, magnesium and potassium oxides together with carbonates help to buffer pH changes. At acidic pH, aluminum oxides and iron hydroxides act as buffering agents. There are some functions. A higher buffer capacity means that the soil can absorb more acid or base without a significant change in pH. In general, clay soils have higher organic matter content, tends to increase buffering capacity. Importance: buffering capacity is important because it helps to stabilize the pH. Changes in pH can affect plants in variety of ways, especially by diminishing the fraction of nutrients in soil that are available to the plants, increasing uptake of undesirable minerals like aluminium. Significance of soil pH is the associated chemical or biological environment of a certain pH is the most important factor. Some soil organisms have a rather limited tolerance to variations in pH, but other organisms can tolerate a wide pH range. Perhaps the greatest general influence of pH on plant growth is its effect on the availability of nutrients for plants. Nitrogen availability is maximum between pH 6 and 8 because this is the most favorable range for the soil microbes that mineralize the nitrogen in organic matter and those organisms that fix nitrogen symbiotically. High phosphorus availability at high pH above 8.5 is due to sodium phosphates that have high solubility. Maximum phosphorus availability is in the range 7.5 to 6.5. Below pH 6.5, increasing acidity is associated with increasing iron and aluminium in solution and the formation of relatively insoluble iron and aluminium phosphates. Iron and manganese availability increase with increasing acidity because of their increased solubility. Earthworms are inhibited by high soil acidity. Earthworms then inhabited the soil under the markings and the soil remaining on the tennis court remained acid and uninhabited by earthworms. Management of soil pH. There are two approaches to assure that plants will grow without serious inhibition from unfavorable soil pH. Plants can be selected that grow well at the existing soil pH. The pH of the soil can be altered to suit the needs of the plants. Most soil pH changes are directed toward reduced soil acidity and increased pH by liming. From the management of soil pH is known to the need of environment, we have to increasing or decreasing the level of soil pH. Lime requirement is the amount of liming material required to produce a specific pH or to reduce exchangeable and soil solution. The lime requirement is the amount needed to increase or adjust pH to a more favorable value. Considered a moderately weathered soil with a pH of 5 for the growth of soybeans, which have a pH preference of 6 to 7. The lime requirement is the amount of lime required to adjust the pH to a more favorable value for the crop being grown. For soybean, it would be about 6.5. If the soil's pH decreases and have 2 to 3, then there can't grow any crop. For this, the soil gets acidic. In the soil we mixed lime. Lime increases the soil pH because lime is a basic component. After that, the soil's pH fixed at 6 to 8. In this pH level, all types of plant and organisms can live. That's why lime is used in the acidic soil. Lime equation. Generally, a minor amount comes from XH unless there is a high or organic matter content. Below pH 5.5, the hydrolysis is of exchangeable aluminium, and between 5.5 and 7, mainly from hydroxy aluminium hydrolysis. The dominant aluminium form at pH 7 is AlOS3, which has very low solubility and for all practical purposes is inert. Lime hydrolyzes in the soil to form OH. CaCO3 plus H2O is equal to Ca2 plus HCO3 minus plus OH minus. The hydroxys neutralize the H plus that are produced from aluminium hydrolysis. Gradually, the exchangeable aluminium and hydroxy aluminium are converted to AlOH3 and the pH increases. The overall reaction representing the neutralization of Al-derived soil acidity is 2AiX plus 3CaCO3 plus 3 H2O is equal to 3CaX plus 2AOS3 plus 3 CO2. Exchangeable and hydroxy aluminium are precipitated as insoluble aluminum hydroxide and the amount of HCl is increased. The reduction in acidic cations and increase in basic cations result in an increase in soil pH. Liming can be viewed as reversing the processes that produce the soil acidity. Now comes soil acidulation. The addition of acid, sphagnum, peat to soil may have some acidifying effect. However, significant and dependable increases in soil acidity are probably best achieved through the use of sulfur. Sulfur is slowly converted to sulfuric acid by soil microbes, and the soil slowly becomes more acid over a period of several months or a year. As with lime, the amount of sulfur required varies with the pH change desired and the soil's CEC. Sulfur is used to change soil pH in a large agricultural fields in arid regions, but it is less common a practice than the use of lime in humid regions. Sulfur is commonly used in nurseries and gardens. Effects of flooding on chemical properties. In well-aerated soils, the soil atmosphere contains an abundant supply of oxygen for microbial respiration and organic matter decomposition. Oxygen serves as a dominant electron acceptor in the transformation of organic substrates to carbon dioxide and water. When soils are flooded naturally or artificially, as in rice production, a unique oxidation-reduction profile is created. A thin oxidized surface soil layer results from the diffusion of oxygen from the water into the soil surface. This layer is underlain by a much thicker layer that is reduced. Oxygen is deficient in the reduced zone, which initiates a series of reactions that drastically alter the soil's chemical environment, as shown in this. Changes in soil pH. From the reaction just side, there is a consumption of H plus and increase in hydrolysis. In most flooded rice fields, iron is the most abundant electron acceptor, and iron reduction tends to increase soil pH. The production of carbon dioxide and the accompanying formation of carbonic acid have an acidifying effect. Alkaline soil tend to be low in available iron, minimally weathered, and the production of carbonic acid lowers soil pH. In acid soil, the abundance of soluble or available iron results in a net increase in pH due to hydroxyl production. As a consequence, flooding of most rice fields causes the pH of move toward neutrality, as showing in figure. There is an increase in nutrient availability, and soils generally do not need lime if they are flooded and puddled for rice production. The increase in pH of highly acid soils is sufficient to reduce the threat of aluminum toxicity, as shown in the figure. Thank you. Stay home, stay safe.